Welcome to Math 106, Chapter 5.1, where we're talking about exponential growth and decay, and then a little bit more about the derivatives of such. So let's take a look at this warm up. Can you find the derivative of the following? Now, before we get to derive your x, notice that we have your power up here. So we need to use the chain rule. Keep in mind the chain rule, right, is f prime of g of x times g prime of x. So that is to say, hey, take the outside derivative first. So everything on the outside, and then we change, and then we can take the derivative of the inside. So let's go ahead and bring that 4 down and subtract 1. So we have the derivative of y is 4 times x plus e to the x cubed. So that is the derivative of that outside function. Now we get to derive the inside. So the derivative of the inside, the derivative of x is just 1, plus the derivative of e to the x is just itself. And there you have the full-on derivative. Lots of things that we've been learning. So then keep in mind what we've learned from chapter, what was that? 4.3, I believe, 4.2, where we talked about the derivative of E, where we talked about, hey, it's itself and then the chain rule, right, with compounding that together. When we take a look at that, when we break it down all together, is that, let's say for your note, that the rate of change of P of t, so that is your normal function, is itself, right? The rate of change. So that would be P prime of t. So if we have a fruit fly issue in your kitchen, the colony will increase at a rate that is proportional to its size. So therefore, the more fruit flies that there are, the faster the numbers will grow. So when we're looking at this P prime of t, this is the rate of change, right? That is what your derivative is some sort of rate of change. How quickly or slowly is it going to be changing, increasing or decreasing? And then it's equal to this k value that we'll talk about here. This is the proportional value to the original P of t. So we have some sort of multiplier here. To the original P of t, because keep in mind the derivative of itself, right? The derivative of E is itself, right? That is P of t times the derivative of the chain rule, right? With your G, that is going to be some sort of a multiplier. So let's say that we have this portion here, right? So if we break it down, we have y is equal to c e to the kt. Then the derivative of it, the c is going to stay, the k comes down, but notice that we have its original function here. So this right here is your y. So y is contained, your original function is contained within your derivative. So if we were to see that out, right, we have some sort of exponential growth when this k value, that is this portion here, your rate, is greater than 0. So if k is positive, we are growing. Whereas we have a decay if k is less than 0. So if k is negative, we are decreasing. And you'll see that over here, right? Where if you take a look at all of your k values here, these are all positive, therefore we are all growing. Now, can you figure out the relationship between this portion here and your written your written function. Well, this is just saying, okay, when x is equal to 0, when x is equal to 0, y is equal to 6. And you'll notice that there is a 6 right here, changing that color. There's a 6 right here. That matches this 6 because if we were to change this to a 0, we have 6e to the 0, which e to the 0, that is going to be 1. So we have 6 times 1 or equals to 6. So that c value that we saw before, c is really your y-intercept. And if we were to see it again, we have this 3 value here, and that matches this one over here. Again, this is when x is equal to 0, or your t is equal to 0 in our case. Your y is equal to 3. Or when x is equal to 0, your y is equal to 1. And you see that right over here, right? That kind of ghost 1 over here that's implied, is that whenever we have x is equal to 0, that is going to be that initial value. So if we are given some sort of an equation here, and we were coming up with, hey, what is the derivative, right? Well, the derivative with just kind of working with what we have. So if we know that the derivative of y is ky, and we might in the future see a problem where we're not really given this whole function, in which case we need to create it. So first thing we need is your k. Your k in our instance is that 2. We also understand that when x is equal to 0, what is y going to be equal to? Well, y is going to be equal to 4. And we can see that very clearly if we were to put in a 0 into your exponent. So we have 4 times e to the 0, or 4 times 1, which is equal to 4. So this 4 here is signifying that this is your y-intercept. So if we were to put it all together, right, this k value here, that k is signifying this 2. This y value here is signifying this whole function here, 4e to the 2x. And you'll notice that this y portion here is going to be found right here. So all together, this should be 8e to the 2x. Let's have you try it again with this k and with this y-intercept. And I'll label it as y-intercept. That way we're not confusing it with the full-on concept of y itself. So in our case, we have k to be 5. You have your y-intercept to be -3. And if we were to come up with the derivative, well, we have 5 times the -3e to the 5t. Now, again, notice that I'm not quite using my y-intercept yet, but in the future, you might only be given a few items, in which case you would need to figure out, hey, how does this relate to this structure here? And kind of work backwards. So we have equal to -15e to the 5t. Let's try it again one more time. K is equal to 4. Y-intercept is 3/2. And your y altogether, we have 4 times 3/2e to the 4a. So we have 12/2e to the 4a, which is 6e to the 4a. Now, keep in mind, this can also be written as, which maybe I should have done previously. We could write this as something like, what structure did they use? They just use y to the 0. We'll just use it like this form, p. We'll just say this is p of 0 is equal to 3/2. or P of 0 is equal to -3, or P of 0 is equal to 4. So just in case you see it, it doesn't shock you in the future. If they're giving you something like this, keep in mind they're just telling you where your initial value is starting. Now that is a smooth transition into when we're talking about some sort of solution for your differential equation with an initial condition. That is to say that this is your y-intercept. Where is your value starting? So the unique solution is equal to y is equal to p of t, your original function of the differential equation with this, again, initial condition. They're going to be telling us in the future that we have some sort of derivative when your initial function starts at a particular value. And again, that's just saying that here. This is y of 0 or p naught. This is just saying that this is the initial value, which is your y-intercept. So if you were to put something all together and they gave you some sort of initial value, they also gave you some sort of k value, you need to work backwards with the two. You need to put the k on top, you need to put the p naught down below, and therefore you have your function as it is. Now keep in mind they might use something like y is equal to c e to the kx as well in your homework. They're just kind of swapping some different, what are these called? Different variables. So your initial, your p naught, this is also going to be, in our case, c. So let's see that in action. It says, let y equal p of t. Denote that the number of fruit flies in the kitchen t days since you observed them. It is known that this species of flies exhibits exponential growth with a growth constant k is equal to 0.3. Suppose that its initial number of fruit flies is 6. Find an equation that models the growth of the function. So you'll notice here that they didn't give you much context, right? But we do know p of t is equal to c e to the kt. Or you could say, and maybe I move this over just slightly, maybe over here, is that p of t is equal to p naught e to the kt as well. So they're saying that your p naught, your initial, how many did we start with? Well, your initial is going to be 6. This is when x is 6, or when t is 6, when you're finally first look at it, you have 6 fruit flies in your kitchen. And they also tell us that your k value here is what? Well, your k is 0.3. So given that you now know the setup of your function, can you create the equation? Well, we have 6 here, e to the k, that is 0.3 t. And there you have it, right? That is kind of why we kept breaking up, okay, this is your y, this is your k, this is your y and your k, right? That way you can create this equation just by working backwards. So you'll notice that k goes up top, y goes in front, k goes up top, y goes up front, k goes up top, y goes up front. So you might not be given this expression, but you're still expected to derive. That's kind of why we were emphasizing that. So if we were to move on and say, hey, can you now estimate the number of fruit flies after 7 days? We now finally have your formula. So now we need to figure out, okay, well, what is your population? What is P of t after these 7 days? So if t is equal to 7, we want to evaluate P of 7. So 6 e to the 0.3 times 7. let's go ahead and plug that into your Desmos over here. So we have 6. Keep in mind, E is found in your ABC format, raised to the 0.3 times 7. So we have 48.99, so about 49 or so fruit flies. So what if we said, hey, at what rate is it now growing? So we can say, at what rate is the population growing after 7 days? Well, when we're talking about that rate, right? Rate is your derivative. And we said, hey, your derivative of t is itself, right? So it's k times p of t. Well, k we said was this 0.3. And let me change that up. 0.3. And p is 6e to the 0.3t. Or you can take the time to do your chain rule, right? We write it all down and then multiply everything by 0.3. So for our case, now we want to know after the 7-day time frame, so when t is equal to 7, we can go ahead and plug that in. P prime of 7 is 0.3, 6e to the 0.3 and 7. Notice that I didn't bother simplifying because we weren't interested in that's not what the question was asking. Hey, derive and simplify. Hey, I just want to know what your rate was. So for us, I'm going to take this portion and now we're going to multiply it by 0.3. That was your K value. So for us, it's going to be about 14.7 or so fruit flies. So about 14.7 fruit flies. So we're going to be increasing at a rate of 14.7 fruit flies per day. Now let's have you try example 3. Now with us not giving you any sort of words or context other than the following. We know that we have the derivative of y is equal to 3 times y, and p and y at 0 is equal to 2. So can you come up with y? Well, if we know that the derivative, right, this is really just saying the derivative of p is really k times p of t, right? So that means that 3 must be k. And this portion here is just saying that this is your initial, right? This is the initial context, initial condition. So that must mean that your P naught or your Y naught is equal to 2. So all together, keep in mind that format. We have P of T is equal to P naught E to the K T. So that means that we have this 2 E to the 3 T. And then of course you can swap your P of T for your Y and so forth. Let's have you try it again with a few more, just really quick examples. I'm just going to give you guys a little bit here. Try that one out, and I'm going to give you one more. So this is your K. This is your P naught. So P of t is equal to P naught e to the kt, which means we have your 5 e to the k t. And one more time, we have k, we have P naught, P of t is equal to P naught e to the kt. Therefore, we have 1, or your ghost one, it doesn't matter, e to the k and t. So hopefully you guys feel comfortable making your own equation given very minimal stuff, or if they give you some context into making it initially. And graphically as well, if you are given just a little bit as well, if you know that your y-intercept, this is your initial, this is P naught. And let's say that as far as your growth rate, let's say your growth rate here is about 4 or so, right? Just kind of giving a very random example. So if we know that this is P naught, right? This is when P is equal to 0 is 2. And if we're given K, then we can say this is P of t is equal to 2 e to the 4t. So let's have you guys try it one more time. A colony of fruit flies grows at a rate proportional to its size. At time t is equal to 0, approximately 20 fruit flies are present. In 5 days, there are 400. Determine a function that expresses the size of a colony as the function of time. So they gave us a few things. They gave us P naught. So initially, there are 20 fruit flies. They also told us that after 5 days, there are 400 fruit flies. And keep in mind, they told us at 0 days, there are 200. We have days and we have fruit flies. And let's see, we aren't given much more, but keep in mind what we do have. We do have some sort of an idea of what your equation should look like. We should have, and I'll actually start from scratch, P naught e to the kt. And so far, we know that your setup should look something like this, but we are also given the context of K or of T and P of T, right? Because this is T and this is P of T. So in that case, P of T, we could say this is really 420e to the K we don't have, but we do have that in 5 days time that your colony is 400 fruit flies strong. That means that we need to come up with a way to solve for K. So we actually know how to do this, given that we have practiced our chapter, I want to say that was like 4.2, maybe 4.4 exercises of how to solve for your exponential function. So here right away, right, let's go ahead and divide 400 by 20, e to the 5k here. So now we have 20 is equal to e to the 5k. Now, how do we undo this exponential? Because k is up high in your exponent and we need to drop it down. So to drop that k down, we need to take the ln of both sides. That'll allow us to cancel the e, right? The same base is needed. So we have ln of 20 is equal to 5k. Divide both by 5. And then we need to figure out, hey, what is k equal to? So let's go ahead and put that into your function or your calculators. So we have ln of 20. Close your parentheses because ln of 20 you can see is a number. It's about 3 divided by 5. So we have 0.59, so about 0.6 or so. Let's just round is 0.6 approximate. So if we were to create an equation for P of t, we have your initial 20, e to the 0.6, that is your k, t. Now we have a few more exercises for you. I will do this one as maybe a separate video, this extra one, but instead let's drop down to example 6, and actually right before example 6. It says the difference between exponential growth and decay is that your exponent is negative. That is, your rate is negative, right? If we're falling, if we're decreasing. Now, we can still use the same exact formula over here, right? It's just your K value is going to be negative. Your textbook, however, shows that it has kind of different, a different variable, which it doesn't matter in the big scheme of things. But if you are somebody that rereads the textbook or uses that to solve some of your homework problems, it's just going to note that this is the negative, let's say that's like lambda or something, P of t. So this just says that decay is a negative k. So let's try out example 6. It says the decay constant for the radioactive element strontium 90 is equal to 0.0244, where time is measured in years. How long will it take for the quantity of P naught of the strontium 90 to decay to 1/2 its original mass? Now, they don't tell us, notice that they didn't even tell us that this is negative. It's implied because they've used the word decay twice in your example. So they have told us that we have the decay value, the decay rate as such. Now it says initially, how much do we have? Well, we know that it decays to originally 1/2 of its mass. So that just means that your P of t is 1/2 the original. Cannot spell original, apparently. One more time. 0.5. So if you start off with 100% of it, right? Initially, you have a whole lot there, right? All of it. And you're going to be decreasing into half of its life. So think about kind of like a pie. I've given you the whole pie, right? And then if I said, hey, like, how long is it going to take for you to take half of its original mass? Well, you're just going to take half of that pie away. So if we are creating some sort of a function, we need P of t. Can you put it all together? Well, that would be your P naught e to the kt. Ours is just going to be the negative, right? So for us, we have, and I'm not even going to keep that negative there because ours we now know is negative. One more time. There we go. So we have 1 e to the negative 0.0244 t, and this is your function here. So if we want to know how long it will take, we need to find t. So one more time, just like before, we're trying to figure out and solve for your exponent up here. So that just means that we have 50% of it left. Go ahead and solve for t. Well, you take the ln of both sides. That will allow you to cancel out your e, and that can drop. So you have ln of 0.5 is equal to negative 0.0244 t. Divide by that. Oops, not t. We need t to stay put. So let's figure out what t is approximately. So you have your function, ln. We said we have 0.5 here inside, and we're trying to divide by negative 0.0244, I believe. Yes. So about 28.4. So 28.4. Now, when we talk about rounding with, especially if t is in years, or any sort of context really with time, is that you've finished your 28th year and you have now started on your 29th year. You haven't finished your 29th year, but you are well into it. So really, we are going to round up to 29 years. So it's going to take us 29 years to get to half of that quantity of strontium, given that we have your decay rate at 0.0244. Now, what we've done is called half-life. We want to figure out what half its life of that element is. Half of a radioactive element is the length of time required for a given quantity for that element to decay 1/2 its original mass. So let's see if you can try that out one more time, where it says a parchment fragment made from animal skin was discovered that about 80% of the 14 C level, carbon level, found today in living matter. Estimate the age of the parchment. Note that carbon-14 is present in radioactive decay. So again, they've told us that we have some sort of radioactive decay, meaning that we are given some sort of rate, and therefore it is negative. So see if you can try it out yourself. Now, they are going to be giving you some sort of these rates. This one is specifically in your textbook on how they found this rate, which is pretty interesting. But for us, I'm just going to be giving you these rates. So if we know that this is actually negative, we are also given that we have P of t is 0.8 or 80% to be 0.8, right? Move that decimal place over twice. We know that P naught, we had initially 100% of it. So if we were to create some sort of an equation, keep in mind, we have this sort of setup. Therefore, if we were to put it all together, we should come up with this particular format. Now, we do not know what T is. This is something that we need to find. And you'll notice that we can right away take the ln of both sides because nothing needs to be divided or come over. So we have ln of 0.8 is equal to negative 0.00012 t. So let's go ahead and divide. So t is approximately, let's try that one more time. I'm just going to swap around some of my things, 0.8. So you'll notice that we don't exactly have half-life because we aren't talking about half of it. We just want to know that about 80% of it is left. And let's see, we have a different decay constant or decay rate. 1, 2. So 18595. 1895. Oops. I already forgot my number. 6. So so it's going to be about 1,896 years old. 1,896 years old. And there you go. Now, I'm going to try this example 5 out as like an extra problem, but that'll be found on the very next video.